Welcome to Study Loop.
Answer to Chapter 13, problem number 53 from the Smith Organic Chemistry textbook. And in this problem, we are given a reaction. So we are told that treatment of anisole with chlorine and iron chloride forms molecule P. We're told that molecule P has mass spec peaks at M to Z equals 142, which is the molecular ion peak, 144, which is the molecular ion plus 2, 129, and 127. And then we are given three pieces of IR spectral data as well. And we are asked to propose possible structures for P. Okay, so later in the textbook here, we will learn that this reaction is actually a named reaction. And so, all right, yeah, well, let's leave that alone. So this is going to be a chlorination, but we should approach this and solve this with the spectral data that we've been given. So we should first look at the molecular ion peak, so M, and M plus 2, so 142 and 144. And since both of these are here, and since we have chlorine as a reagent, this suggests that a chlorination is occurring. So we have a chlorine in our product molecule. Because remember, the two isotopes of chlorine, the two major isotopes, 35 and 37, are each abundant enough that when a chlorine is incorporated into a molecule, we're going to get a peak for each of those isotopes. And they'll be two apart, since 35 and 37 are two apart. And so that's where the 142 and the 144 come from. And then the 129 and the 127, that comes from 142 minus 15 and 144 minus 15. So that's probably as a result of cleavage here. So cleaving off that methyl group is going to remove 15 because that's what a methyl group is worth. And so we can assume that 142 is our molecular mass here. So 142. And so assuming that we're just adding a chlorine to this ring, which is what's going on. If we count up our atoms, so we're going to have 7 carbons, 6 from the ring, and then 1 from the methyl ether. We're going to have 5 hydrogens, 4 hydrogens from the ring if we're saying that we're going to add a chlorine here, or add a position anywhere on the ring, really. So 4 hydrogens from the ring, plus 3 from the methyl ether. So that's also going to be a 7. So C7H7. And then our oxygen is still going to be present, and we're going to have a chlorine as well. So ClO. So if we do the math here, let's see how this adds up. So 7 times 12 for the carbons is going to be 84, plus 7 for the hydrogens, plus 35 or 37 for the chlorine. So let's do 35, and then plus 16 for the oxygen. And so if we add all of that up, we get 91, 126. And so this does indeed sum to 142. And of course, if we were to use 37 instead of this 35, that would be where our 144 comes from. Okay, so that formula makes sense with the mass spec that we've been given. And then we can look at the IR data and try to interpret what the IR is telling us. And so these peaks between 3096 and 2837 wave number, they're going to correspond to CSP3 H bonds as well as CSP2 H bonds. Okay, and we are told that there are numerous peaks in that region, so we can just say that those peaks account for both of them. And then, so these other two peaks at roughly 1600 and 1500 wave number are going to be the result of a benzene ring, a phenyl ring, a 6-membered aromatic ring. So we'll just call this benzene ring. So this the IR data really doesn't tell us anything that we didn't already know. Given all of this information, we can go ahead and propose structures. And since this is all the information that we have, we can't say with certainty at this point where this chlorination is going to occur. So we're going to actually propose 3 structures for this molecule. So with chlorination at each of the 3 possible positions. So ortho, meta, and para. Okay. And para. All right. So as I said, we can't narrow it down any further than that based on the information that we've been given. But these 3 structures do each fit the mass spec and the IR data that we have. And they agree with this formula that we came up with to fit the mass spec data. Indeed, this is the answer. These reagents are going to give a monochlorination of an aromatic ring. And again, that will be covered later in the textbook. And that's the answer to chapter 13, problem number 53.